Thank you, Boumediene, for like this organization of the super cool symposium. So indeed, anamnesic neural differential equation, and we're going to decipher a bit together what I mean by anamnesic here. So first of all, maybe like a motivation of like maybe like my work in general. So I'm interested in like in precision medicine. So basically, when we have like different patients and we try to kind of like target like the right drug that would kind of like really work for that patient in particular. So kind of like individualize those treatments. And the way it works is like you just take like all the clinical records that you have for a particular patient and then condition on a specific drug. Then you try to eventually have a machine learning model or some predictive model that will try to predict like the future trajectory of that patient over time, and then hopefully being able to adjust the treatment. So for dealing with that, we typically use like clinical trajectories. So that's where like dynamical systems come into play. So those will typically be electronic health records, which would be collection over time of like clinical measurements over patients. And those would like typically be like multimodals and also kind of like spread over time with like different sampling. So you may like go in a month like 3 times to the doctor, but then like for some time you also may not see anyone for multiple months. So this kind of like this irregular sampling. So that's the way that like I will represent it here. So given my motivation, I will like consider like irregular sample time series where basically I have like observations over time which are observed like at some given time steps. So for instance here T0, T1, T2. And I will consider that like my observations are just kind of like multivariate vectors with a given dimension. And our goal here, also like a bit more abstract, is like given like this time series, what we would like to have is eventually some kind of like a patient signature. So because like kind of like dealing with like whole time series as a whole, like we would need like operators that we heard before, for instance. But here, for simplicity, we would like to have like a finite dimensional vector representation of that patient. And that patient signature ideally should be very useful for downstream tasks, such as like classification, if you want to do a diagnosis of that patient, regression, if you want to predict maybe continuous measurements, but also for forecasting. So it's kind of like a whole holistic thing. And the way we're gonna assume this, we're gonna model this is that we're gonna assume that like this patient signature is kind of like this hidden health process of that patient. And all the observations that we get are kind of like realization of like that, of measuring that hidden representation. So the way that like one model that has been like quite successful at modeling this type of things is neural ordinary differential equations, which we have heard also during other talks. So here what we're going to assume is that like this hidden health process, so my signature is also kind of like a temporal process that's going to evolve over time, and like the dynamics are going to be given by an unknown ordinary differential equation, and this unknown we're going to model it with a parameterized neural network. And so we're going to try to learn basically how this patient signature, this hidden health process, evolve over time in between observations. So of course, and we like in this class of model, we operate like sequentially, so it's kind of like a more filtering approach. So we go in time, and then like when we observe like a new observations, like we need to update our belief about like where the health process is. So we're gonna have like an integration step, but we're gonna have also an update step that's gonna kind of incorporate those discrete information. And so this update step, like despite being like crucial for being able to incorporate new information, I'm going to show you that like sometimes in this type of approach for like filtering neural ODE approaches, it can lead to some kind of like catastrophic forgetting. So here, like a very simple approach, examples to showcase this behavior. So here I have like it's a synthetic temporal process, dynamical system, and so this is a learn neural ODE over time, where I'm plotting here kind of like the predictions at each time step. So when I'm showing like the prediction here, is basically kind of like what is the prediction of the model given everything that he has seen in the past, right? And so you see that he's doing like a pretty good job. He has seen quite a lot of training examples, and he's kind of like being able to predict pretty well. But then what I'm going to try to do is that like when I'm here, I'm going to try to integrate the ordinary differential equation that I have backwards to try to see like if actually kind of like remembers what has happened in the past, and this happens. So this, you see that like basically it's kind of like pretty good in between the observations, but as soon as he has like to process the fact that he had an update here, he kind of like completely forgets what has happened in the beginning. And so this is kind of like problematic in a sense, because it's kind of like, it can point out like the fact that like the neural ODE kind of like forgets about like what has happened like at the beginning of the temporal process of the time series. So in this work, what I'm going to try to do is kind of like show you a method that we developed to actually solve this issue and kind of like have almost a perfect reconstruction, like with a different architecture of neural ordinary differential equations. And for this, we're actually going to use orthogonal polynomials, which were just kind of like mentioned right now. So, which is an idea like taken by like this state space modeling, which you also discussed. Yes. Yes. So the way that like you incorporate the information is like update, like this is learned as well. Yeah. So maybe to make it slightly more concrete, so we're gonna try to develop like this more neural ODE architecture, which has like these three objectives. So it should have like a long-term memory representation, which also resonates with the talk we had before. It should also be able like to have good downstream performances. So if I mean that like when I train this model just to, let's say in an unsupervised way, just to predict the like forecast ahead like this time series, I want like this representation, this patient signature that I get at every time step to actually be pretty good at predicting other tasks which we're not trained upon. And then it should also be good at forecasting, but we're going to train it to forecasts. But we don't want to lose that ability. Okay, so I'm going to do like a very short maybe recap on orthogonal polynomials, just like to get like everything that we need. So basically, as probably most of you are aware of, so basically we have a basis of polynomials which are orthogonal with respect to each other according to a given measure that we call mu here. And so depending on the measure that you're going to choose, you're going to generate like different bases of polynomials. And so basically like different measures, like if you have like just the square functions, you would have like Legendre polynomials, so that's just between 0 and 1, Laguerre polynomials, and Hermite polynomials, as we said, if we want, if we have like just the Gaussian measure. So the nice thing about this is that like they give us some optimal reconstruction when we project, for instance, like our temporal signal, like say f of s. If we project it against this basis, we know that like this projection is actually optimal with respect to the reconstruction with respect to that measure mu. And so choosing that measure mu will also like give us, here I show an example of like where do we care about our signal, right? So like if we just took like the classical Legendre polynomial between 0 and 1, and we try to do this projection, we're going to have like a very good fit between 0 and 1. But we're going to actually diverge in the other direction. And same for Laguerre, where we have like this kind of like weighted thing over time. So that's all good, but what we would like to do, and what was developed actually in the Hippo framework, is being able to like update this measure over time, right? Because like as I said, we kind of like incorporate information as time goes by, and so we would like not only to remember like something between 0 and t, but we would like to actually have like that window sliding over time. Right? And so kind of like this time-varying measure is going to generate like time-varying polynomials, which are going to give us like a different projection every time. So the quantities we are interested in here in these projections are the coefficients here, because like the basis is actually going to be, I mean, something that we know, we can just like compute it. The thing that varies is kind of like the signal that comes into play in like as input. And so it's a good candidate for kind of like summarizing having this patient signature, if you would have like this or input signal arriving continuously over time, would just be to compute like those polynomial coefficients. Yes. 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 So here right now, I'm kind of like step a little bit aside from the patient case. I'm considering I have just like a continuous signal, like for instance here f of s, right? And so like as time goes by, I observe more and more of that patient. So basically I kind of like sliding my window over time. And so this allows me basically to kind of like remember, like, let's say if I use like the typical Legendre polynomial that I scale, like the last 1 second, for instance. Of course, then I can scale the window and stuff. I can remember the last 10 seconds or something like this, instead of just focusing just on like on a specific, like between 0 and 1 second. Okay, and so basically those are like the quantities that I'm interested in. And so the remarkable thing is that like, so those coefficients actually follow a very simple linear ordinary differential equations, which is given here. And so like that gives us kind of like a very good candidate like system of ODEs for basically kind of like updating like our patient signature over time. If we would have like some good like, yeah, input signal, like a continuous input signal here. But here, so one thing is that like, so this input signal, so we don't really have that in practice because like we actually would try to predict it over time. So we would like, kind of, when we do like this, when this forecast, we would actually want to predict this. And also, as we have like irregular sampling, we would want also to, like, we don't have like continuous observations of like in between the different observations. So this could be also solved by kind of like using like different integration, like integrating, let's say for a trapezoidal rule or something like this between observations. But we're going to try also to see if we can get like an additional boost by kind of like maybe predicting a bit better what's going on in between the observations continuously. So the idea that we're going to have here is kind of like mixing this system of ODEs given by like the temporally evolving coefficients of orthogonal polynomials with a neural ODE, which we're actually going to learn the forecasting dynamics and like mix them together. So that's like a construction that we call poly-ODE. And so basically here I'm like, yeah, we're retaking the same. So we're gonna have like just like as a typical neural ODE, so a readout function that we learn that kind of like basically learns the observations given like this hidden process, and we model this hidden process with a system of ordinary differential equations. But now we're gonna like structure the system according to like a combination of like this EPO type of system of ODEs and like a more like regular type of neural ODE, which kind of like incorporate like the learning and the forecasting into it. And then we also have like an update step as before. So all in all, like we have like this architecture that allows like to basically forecast over time, but then do also the reverse reconstruction, and we use like the coefficients of the orthogonal polynomials as kind of like our patient signature that can allow us to do like some downstream predictions. So we can show with this that we can like can use this construction like to show like some theoretical guarantees. So it's kind of like a little bit complicated like expression, but in terms of like the reconstruction that we have and like in the true signals. And we see that it depends kind of like on the smoothness of the signals, the number of coefficients that you take, of course, but also the number of observations, because at the observations you will have like some little discrete updates, which will also kind of a little bit degrade the reconstruction error. Yes. Yes.
So this basis is actually moving. Is that correct?
Yes. So basically, I'm defining. Yeah. So in this architecture, in the experiments, I only used like a Legendre that I kind of like shift, and I decide like so. Here, like in the other expression, delta is basically the length of like of that window. I'm constructing what I'm caring about. And actually that's something that I would like also, so here it's kind of fixed, this measure. So I think what would be also interesting, but I haven't found like kind of a very nice way of doing that, but like kind of like, can you also maybe learn a way kind of like a measure that will give you also some kind of like interpretable way of like figuring out where things are important in your signal. Exactly, which actually you yeah. I think there was another question. Or?
Yes. I don't want to interrupt the flow. But in essence, you are learning this, you are maintaining a memory of these coefficients C corresponding to a fixed level grid polynomial over your backward time.
Yeah.
And then reconstructing the actual signal by just linear combination of coefficients multiplied by polynomial at each instant.
Yeah, so basically the reconstruction I can just do by indeed like then, yeah.
Exactly, and then when you feed that back into the neural ODE, you get that, you get an information on how each time neural ODE was updated, what input signal updated to neural ODE to be able to trace everything back again.
Yes, I'm really using those coefficients that I kind of like store as like the memory of my signal because that's what they are, and kind of like this kind of like is my hidden state that can allows me like then to forecast ahead. Yeah.
So you have a memory of information based on which you can forecast. So depending on how long you look at the past, how many coefficients you keep in the past, you can forecast to that accuracy in the future.
Right. So the number of coefficients is actually independent on the length of the time series, right? Because so basically I consider I have n polynomials, for instance, then I will update those n's over time continuously.
Yeah, the number of time instances you keep these coefficients for.
Right, yeah.
Thank you.
Sure. Right, and so that's, yeah, and for instance here you see that like the delta also comes into play. So if you have like a larger delta, which is like basically the width of my polynomial, it's like the reconstruction is also worse. Yeah, and so then basically like giving that, like I still kind of like have like this good, let's say construct like this mix of like this new system of ODE like allows me like then to like keep like this really nice forecasting ability. So it's still like being able to forecast over time. But at the same time, I kind of like ensure now that like I remember also everything about the past of that time series, because like when I reconstruct it, basically I can almost perfectly get the history. So in terms of experiments, so I try like with different first like synthetic slash semi-synthetic experiments, and then I use also healthcare, I will show later. So we can see that like, yeah, in terms of like, I checked in terms of like downstream classification. So here I was like creating a label for each of like the different time series. So, and the label was never seen during training. So I was like really trying to see if like the information content that I learned just from like this unsupervised like forecasting actually was useful. And then like a backward reconstruction as well, which I'm just trying to see if like the reconstruction that I get like matches like with the past of my time series. And then so I basically compare with like different ODE type of flavors, but also like with this EPO network, which is basically what's like this original line of work, which like propose also like to use this basically state space models like based on like those sliding windows of like orthogonal polynomials. And so we see that kind of like we're close like to S4, but like when like with other EPO RNNs and EPO observations, like we see that basically it seems that the fact that we can basically leverage the whole data set to figure out like what's in between observations. So not just looking like this trapezoidal integration between like all the two observations, but like really being able to model the whole model continuously and like feed that into this construction kind of allows like to get better results. And so another experiment that we're like doing, so like to jump back also maybe to this original motivation is like using the MIMIC data set, which is like a very well-known kind of like healthcare data set, which is like patients in the intensive care units, where you have like time series of like different vitals. And here, for instance, I use heart rate, mean blood pressure, oxygen saturation. And then you can see here first that like, yeah, the reconstruction that you can get are like pretty good as well. So of course, so like you already kind of like ensure that like it at least lasts some trends or important trends kind of like embedded into this patient representation. But then also in terms of forecasting, reconstruction, and classification, it's kind of like on par with other kind of like state-of-the-art ODE type architecture for this type of methods. Cool. So maybe before wrapping up, so here you can keep track of like kind of like your the prediction of your models, of your forecast over time. But also nothing prevents you, if you have like a model that can also give you uncertainty, that like you can also kind of like accumulate uncertainties. And so like give you also a notion, overall notion in your patient signature of like how certain you were about like kind of what happened to a patient in the past. So basically you can accumulate this uncertainty. And so this is useful also in, let's say, healthcare applications when you want to know whether you can trust a patient signature or not. And here you can see that like basically in terms of like, correlations between like the uncertainty that you accumulate through those signature and let's say the reconstruction error, you see that like, so it correlates pretty okay. So to conclude, so what we proposed is kind of like trying to an attempt to have like a neural ODEs, which would display some kind of like long-range memory, like the same thing that like those SSMs and S4 have displayed, but more with like a typically more, let's say, neural ODE type of flavor. And so which would give like this, like address like this amnesic behavior that were displayed in like those neural ODE architectures. So we use that like with orthogonal polynomials. And we integrated the dynamics that we saw from like the EPO orthogonal polynomials with a typical neural ODE architecture. So in terms of like, future works, other ideas, so as I said, like indeed, and as we just discussed, like the measure here is like kind of like chosen. So it could be also maybe an interesting kind of like data interpretation avenue, like to try to like learn also the metric, like which would be like the most useful for a particular problem. So how can we learn it? I think it's actually quite difficult. So also could we, so right now, like this architecture is kind of like fixed in a sense that like, so I don't really, let's say, learn anything in like in that orthogonal coefficient matrix. So like this matrix A here. Which they do, like in SSMs, for instance, because like it's kind of like they initialize it with that and then they kind of learn it. So, I mean, other experiments would be useful in kind of like trying to make this matrix also learnable. And then also there is like this cost of like this keeping track of like those coefficients, because like for each input dimensions of your process, you need to choose like to have maybe like n orthogonal polynomial coefficients. So like, it will grow. So if you have d dimensions, it will grow by, it's going to be n times d. So you start having like very large hidden dimension in your process as well. So is there a way maybe, so I've read a few papers about that, but I would be interested if like someone knows something more, to how to model maybe like multivariate process into like a single, so basically having kind of like a basis of like a multivariate polynomials as well. So I'm not sure exactly computationally how, how tractable that would be or something like that. But kind of like leveraging also like the correlations between different channels. So when you have heart rates, for instance, let's say like heart rates and oxygen saturation, like if you know beforehand that there is like some correlations between the two time series, like how can you basically leverage that better? Because for now, in terms of like the number of dimensions, it is not leveraged. So so I want to thanks Rahul Krishnan, which was the host of like my little internship during I worked on this, and also other collaborators. Thank you so much.